Hi, in this video we will consider strategies for solving polynomial and rational inequalities. We will present a set of general guidelines followed by a variety of examples. First, rewrite the inequality so that the right-hand side is 0. Next, completely factor all of the polynomial expressions. Then find the key numbers where any of the polynomial factors equal 0. Place the key numbers in numerical order on a number line. This will divide the number line into a series of intervals on which the expression on the left-hand side of the inequality cannot change signs. Now test the sign of each polynomial factor on each resulting interval. Finally, determine the solution to the given inequality. Of course, examples will help to clarify this process. Solve the inequality x squared minus 4x plus 3 less than 0. Notice that we have a quadratic inequality. We can factor the quadratic expression as x minus 3 times x minus 1. The key numbers are numbers where any of the factors equal 0. Thus, in this problem, the key numbers are x equal 1 and x equal 3. Now we draw a number line and place 1 and 3 on it. This divides the number line into 3 test intervals, namely the intervals from -infinity to 1, from 1 to 3, and from 3 to infinity. We test the sign of each factor on each of these intervals by choosing one test number from each interval. On the interval from -infinity to 1, we choose the test number x equals 0. Both factors have negative values for x equals 0, so the product x minus 3 times x minus 1 is positive on that interval. On the interval from 1 to 3, we choose the test number x equal 2. At x equal 2, the factor x minus 3 is negative and the factor x minus 1 is positive. Thus, the product is negative on the interval from 1 to 3. Finally, on the interval from 3 to infinity, we choose the test number x equal 5. Both factors are positive when x equals 5, so the product is also positive there. Now we need to interpret this sign chart to answer the original question. We want to choose where the product is negative. Therefore, the inequality x squared minus 4x plus 3 is less than 0 on the interval from 1 to 3. Let's look at more examples. Now let's solve the inequality x to the 4th less than or equal to 12x cubed minus 35x squared. Notice that the given inequality does not have the right side equaling 0. We can add or subtract on both sides to produce 0 on the right-hand side. It's difficult to determine when a sum is negative, but relatively easy to determine when a product is negative. Therefore, we factor out the monomial x squared. Notice that the other quadratic expression will also factor further. Thus, we want to solve the equivalent inequality x squared times x minus 5 times x minus 7 less than or equal to 0. The key numbers in this problem are x equals 0, 5, and 7. Now we draw a number line and place the key numbers 0, 5, and 7 on it. This divides the number line into 4 test intervals, namely the interval from -infinity to 0, from 0 to 5, from 5 to 7, and the interval from 7 to infinity. We test the sign of each factor on each interval by choosing one test number from each interval. We choose convenient test numbers. Notice that the factor x squared is always positive. The factor x minus 5 is negative until we pass x equal 5, and then that factor is positive. Similarly, the factor x minus 7 is negative until we plug in test numbers bigger than or past x equals 7. We can compute the sign of the product by counting the number of negative factors. An even number of negative factors produces a positive product, while an odd number of negative factors produce a negative product. We want where our product is negative or equal to 0. Thus, we need to include the key numbers where the product equals 0. The solution, then, is the interval from 5 to 7, including the endpoints, union the set that contains only the element 0. For our third example, let's switch to a rational inequality and solve the inequality x plus 4 over the quantity 2x minus 3 greater than or equal to 0. Although it is tempting, we don't want to multiply on both sides by 2x minus 3 to clear the fraction. Remember that when we multiply an inequality by a positive amount, the inequality sign remains the same, but when we multiply an inequality by a negative amount, the inequality sign reverses. Because we don't know the sign of 2x minus 3, we wouldn't know whether or not to reverse the inequality sign. Instead, we will utilize what we know about when a fraction is positive, negative, 0, or undefined. To review, a fraction is positive when the numerator and denominator have the same sign, and a fraction is negative when the numerator and denominator have different or opposite signs. A fraction is 0 when the numerator is 0, and finally a fraction is undefined when the denominator is 0. In this particular fraction, the numerator and denominator are already as factored as we can get. So the key numbers, where the numerator and denominator are 0, are therefore the numbers x equal 4 and 3/2. Now we draw a number line and place -4 and 1.5 on it. This divides the number line into 3 test intervals, namely the interval from -infinity to -4, the interval from -4 to 1.5, and the interval from 1.5 to infinity. We test the sign of each factor on each interval. Again, we can choose convenient test numbers from each interval. Notice that the numerator x plus 4 is negative until we input a test number greater than x equal -4. Similarly, the denominator 2x minus 3 is negative until we pass x equal 1.5. We can compute the sign of the quotient by counting the number of negative factors. We want where the quotient is positive or equals 0. Therefore, the solution is the interval from -infinity to -4, including -4, union the interval from 1.5 to infinity. Notice that we include the endpoint at x equal -4 because the fraction is 0 there. We don't, however, include the endpoint at 1.5 because the fraction is undefined there, and hence 1.5 is not in the solution set. Let's consider a final example that might be a bit more involved. Solve the inequality 1 over x minus 2 minus 1 over x minus 1 greater than or equal to 1/6. This time we don't have the right-hand side equaling 0, and we also don't have a nice single fraction on the left-hand side. When we subtract 1/6 from both sides, we now have a sum greater than or equal to 0. This is not an easy problem because there are infinitely many ways a sum can be positive. We want a single fraction on the left-hand side. So we get a common denominator and then simplify the numerator. We end up with a single fraction, but we have a negative leading coefficient in the numerator and an extra factor of positive 6 in the denominator. We can clean up both of these by multiplying both sides of the inequality by negative 6. Of course, when we multiply by a negative, we have to reverse the inequality sign, and then we also distribute the negative in the numerator. Now we can factor the quadratic in the numerator, and we have an equivalent but solvable problem. We want to solve this inequality with the numerator and denominator already factored. And we want where the rational expression is non-positive, that is, where it is negative or equal to 0. Since everything's in factored form, the key numbers are easily identified as x equal 4, 2, 1, and negative 1. We draw a number line and place the 4 key numbers on it in numerical order. This produces 5 test intervals. We test the sign of each factor on each interval by choosing a convenient test number from each interval. Notice that the factor x minus 4 is negative until we plug in test numbers greater than 4. Once we pass x equal 4, the factor x minus 4 is then positive. Similarly, the factor x plus 1 is negative until we pass the key number x equal negative 1. The factor x minus 1 is negative until we get past or greater than x equal 1, and then it's positive. And finally, the factor x minus 2 is negative until we pass x equal 2, and then that factor is positive. We can again compute the sign of the final expression by counting the number of negative factors in each row or on each interval. We choose the interval on which the expression is negative and include the endpoints where the expression is 0. We won't include the endpoints where the expression is undefined because those points are not in the solution set.